Okay, next, so we've seen the connectives, we've seen the quantifiers, but we haven't seen equality, which is a very important symbol in logic. And equality behaves a bit differently because even though its result is a proposition, the arguments of inequality can be arbitrary objects, right? So you could compare two natural numbers or other objects. So that makes it a bit special, and that means we treat it specially. It has the properties are quite different from the intro and Ilm rules that we saw above. In fact, the key four properties are called reflexivity, which here is stated as a lemma, which says basically that you have A equals A for all A. And this is the basis of the Refel tactic, right? This EQ.Refel lemma. Then you have symmetry, right? That if you've proved, I'm going to use letters again, right? So if you've proved A equals B, then you also have B equals A. You have transitivity, AB, BC implies AC. And you have substitutivity, which is hard to pronounce. Here, yeah, this is harder to read, but it's worthwhile to take some time to think about it. So this here is an arbitrary context in some sense, right? You can think it's a variable applied to a variable. So this can be instantiated by arbitrary lambda terms that will then get beta reduced because you have an argument here, right? So you can think really of this as some arbitrary term that contains some M4, you know, one or more or zero or more instances of M4, occurrences of M4 in it. This is the proper way to read something like this in a higher order logic, such as dependent type theory. And this is something that's explained with more care in the Hitchhiker's Guide. But here again, you have, this is the same term as here, if you like, or the same proposition, except that some occurrences of M4 might be replaced by M3, right? But otherwise they're equal and syntactically equal. And then we have that M3 equals M4, right? So this basically says that if you have this equality here, and you have some term that may contain some occurrences of M3, then you can replace all these occurrences of M3 by M4 in the term. That's what it's really saying, okay? But we'll see it in action. Again, we start with the difficult stuff first, and then it gets easier when we see it in action. So we want to prove something like this. We have, let's see, we have that A equals A prime. This is the hypothesis. And we want to prove that FAB equals FA prime B, right? So basically we want to rewrite this A into A prime. And yeah, actually we can, you remember we had this EQ subst here, which takes an equality. Well, here we use that equality. The equality is A equals A prime. And the context around it is FB, right? So this is what the M2 here represents, is FB, or actually a lambda term, you know, lambda x FXB. And once we've applied this rule, then we're done. I mean, we just have to apply reflexivity. So here we do it the tedious way. We can also just write Refel if we want as a tactic. But right now, I'm just showing how these lemmas can be used. So I'm going to use Refel. Here's a more complicated example where we have, you see, FAB equals FA prime B prime, and we have two equations to help us, all right? And here we just apply the rule twice. You know, the first time to rewrite actually we write A prime to A, and then B prime to B. That's the direction in which it happens. And then at the end, we just have reflexivity and we're done. Okay. Now, you know, this is a bit tedious, this whole apply, eq, subs, blah, blah, blah. So there's a tactic called rewrite. And this one really goes left to right. So here we're rewriting A into A prime. So you see, I say rewrite using this equation. So this says, find one place where you have the left-hand side of the equation and replace it by the right-hand side. Only one place. And then you do the same here with B. And then rewrite is smart enough, it will apply refl automatically, so we don't need to do a refl here. It's already done. Once it notices that the two terms are equal, it just does it. Here's another example. So I think we saw an example like this before. Well, I think exactly the same one. And if we don't like these negations, they're confusing us, then we can unfold the definition of not. And there were two nots, so I unfolded both now. And now we see more clearly in some sense, right? We don't have these negations to bother us. All we see is the implications and the false. So then it's usually, it's often easier than to, yeah, and I don't need this step. I don't know why this step is there, because we've unfolded the knots. Okay, to do, remove me, right? And tack. The rest of the proof is as usual. So we've learned RW, which stands for rewrite. There's another rewriting tactic, which is called simp, which is used, I think, even more often. I think both of them are very useful, but simp is probably the most useful one. And what simp does is it exhaustively rewrites with a set of lemmas. So it's not just one lemma at the first spot where it matches. It will just exhaustively apply all the lemmas that you specify, plus a set of pre-specified lemmas, so standard lemmas, you know, about addition, about, well, I mean, we haven't seen much of Lean, so I cannot refer to those things, but, you know, about basic things that are in Lean, and we can even register our own so-called simp rules using an attribute that's called @simp. So you see here, I have a 1 + 1 on one side, I have 2 on the other side. Well, simp can do that. I don't need to state the equation 1 + 1 = 2. So I can, in one line, just say simp using the two hypotheses, and you know, everything you know, including the fact that 1 + 1 = 2, and that, you know, deals with this example, which is a generalization of the example we had earlier, right? So rewrite and simp you're going to use very often. These are also very important ones. That's why we cover them in lecture 2, right? So this course has is built on the principle that important stuff comes first, and then less important things appear later. So I wouldn't bother with tactics that you're not going to use often in lecture 2. That will come in lecture 11. Okay, then there's another one, another tactic that works very differently, but it's also about equalities, and it's it's called CC for congruence closure. So congruence is this idea that, you know, if A = B, then f of A = f of B, right? So your equality, they still hold when you add some contexts. So that's what congruence means. You know, in mathematics, that's a very common word. And the congruence closure, in some sense, computes, you know, all these possible combinations of contexts and so on. It's a very nice algorithm. And it's implemented, yes, in CC, and it will pick things up automatically for you, right? So here you have these two equations in the context, you have this goal, and CC can just see, CC can just see, wow, that, you know, these must be equal. The construction, the congruence closure puts, you know, A and A prime in the same equivalence class, B and B prime in the same, you know, equivalence class, and then because there's a closure, then these terms which are built on those also end up in the same equivalence class, the left and right hand side, and that means they're equal. All right, and CC has a, you know, it's very nice to sometimes to reason about equalities. It's also has another magic power, and often we use it for one and often for the other one, and sometimes even for both in combination, is the fact that it knows that binary operators are, you know, usual ones, addition, multiplication, and so on, are associative and commutative. So in particular, if you have a goal that looks like this, where, you know, ABC, CB, A prime, right? I mean, A would also work, obviously. So it doesn't matter in which order the pluses, I mean, the arguments to the pluses are, and it also exploits, you know, just like in the previous example, it exploits any inequalities that are around. So the congruence closure is, you know, up to, we call it AC, associativity and commutativity, which makes it quite powerful. So AC in particular is it's very hard to predict when it's going to work, you know, unless you know the congruence algorithm, you know, very well. And I mean, even I've read the scientific paper about it, and you know, I still cannot predict when CC will succeed or not. But often CC saves me from having to write several lines of boring proofs. So I mean, you don't have to use it. There's, I think, nowhere in the course where you absolutely have to use CC, but it's a useful tool, you know, to finish easy proofs in some sense. Easy in your mind, but of course they would be very tedious if you didn't have CC. So here, I think this is where even more than for any other tactic in this lecture, this is where I would say, you know, don't panic if you don't understand what congruence means or closure or whatever. I mean, this is just a tool you can use or not, and if it helps you, so much the better.